In this video, we'll be talking about area between two curves as a first application of integrals. So one of the first applications that one comes across in talking about integrals is the idea of area between two curves. In particular, the idea of finding areas of regions in the plane and how to do that using integrals. So there's a certain region of the plane that's really easy to find using integrals, and that's one like this. If I have a function f of x and I want the region between that graph and the x-axis, well, I know how to find that. That's just the integral of the function f. So if this went from a to b, I would find this area by just integrating f of x over that range. That's a region of the plane that's pretty easy to find the area of using integrals because that's the definition of the integral from a to b of this function f. We can do something a little more general than this that isn't too much harder to see. And the idea there is, what if I have two functions and want to find the area between them? So I have two functions f and g, and say I want to find the area of this region in here. Well, how can that be done? Well, it's pretty easy to see that if I continue these lines down, if I look at the integral of f, that'll give me the blue part plus this green part down here. And if I look at the integral of g, that gives me just the green part. So if I subtract the green part from the blue and the green part, I'll just get the blue part back, which is the area that I want. So I could find this area by taking the integral of f and then subtracting the integral of g, which gives us something like this setup here. And because of how integrals are linear, we can put these two together to get a single integral out of this, which means the area is the integral from a to b of f of x minus g of x dx. And for this type of setup, this formula is always true. If I have one function that sits on top, one function that sits on the bottom, and I want to find the area between those two graphs, I can always do so via this formula. The picture I drew here has them both positive, but if they were both negative, you could just shift them up so they are both positive, and you get the same area formula that way. The area doesn't change if I shift the whole graphs up or down, so I can use this formula no matter what the functions are to find the area between these two curves over this range from a to b. And this assumes the function f is on top always and g is on the bottom always for this situation. So regions like the one described on the previous page are called vertically simple. What do we mean by that? Well, we mean that the region is one such that there is a single function sitting on top of the region the entire time and a single function sitting below the region the entire time. That is, I have a function f and a function g such that my region is the area between some points a and b in the x direction and f on top, g on the bottom. So the region is sort of written in this form. It is all points in the x-coordinate between a and b, and the y-coordinates between g of x and f of x for those two functions f and g. Right? Something like here's a, here's b, and I have my function f that sits on top, my function g that sits on the bottom, and that gives me a region. Something that would not be vertically simple is something like this. So this region here is not vertically simple. If you look at it, there is not a single function on top the entire time, right? For the first part, this function here, the straight line, is on top, but for the second part of it, this curved segment here is on top. So there's not a single function on top the entire way, so it's not vertically simple. Only for these vertically simple regions do we have such a nice formula for the area between two curves, just the area of, or the integral of, the top one minus the bottom one. As an example on this, find the area between the graphs of y equals x plus 1 and y equals x squared plus 3x plus 2 over the interval 1 to 4. So we'll start by drawing the graphs of these functions. Y equals x plus 1 will be a straight line that crosses the y-axis at 1. This parabola here factors as x plus 2, x plus 1. So it's going to cross the x-axis at minus 2 and minus 1, the minus 2 and minus 1. For x equals 0, it hits at 2, so up here, something like that. So the region we're looking for is between 1 and 4, the area between these two curves. Now from the picture, we can see that the parabola is bigger on this domain. We could also see it by plugging in some numbers. So if I plug in x equals, say, 2, for the straight line, I get y is at 2 plus 1, which is 3. The parabola is at 4 plus 6 plus 2, which is 12, which is bigger, so the parabola sits on top. That means to find this area, I want to integrate the top function, the parabola, minus the bottom function, the straight line, between 1 and 4. Integrate from 1 to 4. the parabola minus the straight line dx. And then we just simplify this out and solve. We get x cubed over 3 minus x squared plus x for antiderivative, and now we can just plug in our numbers. 64 over 3 minus 16 plus 4 minus 1/3 minus 1 plus 1. 63 over 3 is 21. We get 21 minus 16 plus 4, which is 9. So that's how you'd find the area between these two curves, and that's how you can find the area between two curves for any vertically simple region set up like this.